Today I would like to show you the latest version of my 3D printed modular rotary switch. It has 8 switching positions in total and controls up to 4 of these conventional micro switches, which are triggered by a cam wheel in each switching plane. These micro switches are specified for switching up to 5 amps and 250 volts, so they are useful for a wide range of applications. This particular rotary switch has built-in stops and uses only 4 of the 8 possible positions. From the middle position, 1 step to the left and 2 steps to the right. This is the characteristic I actually need, so I'll go into details about this one in a minute or two. But as I said, it has a modular design. Just out of curiosity, I assembled this example. It has 3 switching planes with a total of 12 micro switches. And it goes all around over all 8 positions without any stops. I left out 2 of the micro switches here in the middle of the device, so we can hopefully peek inside and see how the switches are triggered. I'm not going to push it any further, but I can say that the haptics and the switching feeling didn't degrade with the additional planes, so I think it could be extended even further without any problems. But now back to the smaller version. Before I go into more details of the switch, let me explain for what I need it, what it should actually do, and why I can't just use a standard rotary switch from the electronics store. It all started with another project idea, an adjustable isolation transformer, an essential device for testing or repairing any mains-powered devices, like for example ancient CRT-based TVs. Okay, so the design of this isolation transformer consists of a simple toroidal transformer with a 1:1 ratio, which is obviously responsible for the isolation part, and an adjustable one-coil transformer or variac for the regulation feature. In German it is called Spartrafo. It's adjustable but not isolated because it has only one coil used for both primary and secondary side. So in combination it's what I wanted, an adjustable and isolated transformer. But I don't want to wire them together in a fixed manner. Instead I want to use them in different combinations. Here is the wiring diagram I had in mind. The primary side of the toroidal transformer is connected to the mains power via the main switch A. On the secondary side, it should be possible to bypass the one-coil transformer, here with switch B in position 0 and switch D in position 1. The opposite positions of B and D then includes the one-coil transformer, which again has 2 input options. Switch C in position 1 uses the whole coil as input, which means that the highest output voltage is equal to the input voltage. However, when switch C is in position 0, a reduced number of windings is used as input, and therefore the maximum output exceeds the input voltage and can be adjusted up to about 260 volts. So the whole device should have 3 operation modes and 1 power off mode, realized with 4 individual switches that I want to control with 1 rotary switch. Commercial rotary switches typically just have 1 or 2 input poles that are sequentially connected to one of the output throws. That's not what's needed here, and that's basically the reason for this whole rotary switch project. The first decision was to have 8 switching positions in total, which means a 45-degree stepping and resulting in this basic structure of 8-sided pyramid-shaped elements that fit into each other. The whole construction is divided into planes. First, there's at least one switching plane. It consists of a cam wheel which is coded according to the required switching sequence and triggers the 4 microswitches located around it. Then there is the stepping plane, which is responsible for the overall haptic feeling and makes sure that every switching position snaps into place. This is done with such a gear-shaped stepping wheel and 2 also 3D printed springs. I've experimented a lot with this module and tried springs with different thicknesses. At the end, I liked the springs with a thickness of 0.8 millimeters and good lubrication with silicone spray the most. But that is probably a matter of taste. I also tried springs with 0.65 and 0.5 millimeters thickness, which provide 2 less mechanical resistance in my opinion. But I strictly recommend the lubrication with silicone spray, otherwise you feel and hear the grinding of plastic against plastic, which isn't nice. This stack of modules is finalized with a cover plate with 2 mounting holes for the rotary switch. The construction is completed with an additional pyramid-shaped cone element, providing a proper distance between the cover plate and the knob. To prevent the knob from falling off, as it happened quite easily with my previous rotary switch design, it is secured with an M3 screw and a nut that fixes it to the stepping wheel. But now let's focus on the switching plane again and how to get the configuration for the isolation transformer. What we need first is a truth table with the switching positions for this schematic. Let's start with position 0, which is the off state. Switch A must be open, which is marked as 0 here, while all the other switches are not relevant, therefore marked with an X. In all other positions, switch A must be closed, so we can already mark them with a 1. Position -1 is when the knob is turned one step to the left. This is the bypass mode, where switch B must be 0 and D must be 1 according to the schematic to bypass the 1-coil transformer. Switch C isn't relevant here. In the remaining positions 1 and 2, for normal and boost mode, the variac is in use and therefore switch B needs to be 1 and D must be 0. Now only switch C is missing, which must be 1 in normal mode and 0 in boost mode, where a reduced number of windings is used for input. I want to have all 4 switches in one plane, so we have to figure out the proper coding of the cam wheel to meet the required truth table. After some trials and errors, I came across with this switching wheel. Let's quickly write down the switching states of all positions for the 4 switches, which are now marked with north, south, east and west, according to their location inside the switching plane. Okay, the coding sequence of this cam wheel is 0, 1, 1, 0, 0, 1, 1, 1. Obviously, this coding sequence is effective for all the switches, but with a phase shift of 90 degrees or 2 steps from one switch to the next. So when it hits the north switch directly at position 0, then it hits the next one, which is the east switch at position 2, then the south switch at position 4, and finally the west switch at position 6. By moving the overhangs to the related gaps above and adding the position -1, which is equal to position 7, we get the complete states table. Now the top part of the table from position -1 to position 2 should correlate to the truth table. And luckily it does. What a coincidence! The sequence of 1011 of the north switch fits to switch A from the truth table, so we can already mark the north switch with an A. 0011 of the south switch fits to 0x11 of switch B. 1110 of the east switch goes with XX10 of C. And finally 1100 of the west switch correlates with 1x00 of switch D. That was probably the hardest part. Now for some more construction details. If the rotary switch needs stops to prevent it from turning all around, this is also done in the stepping plane. I've designed variants with and without stops. This is the variant I'll need for the isolation transformer with a 180-degree stop allowing only 4 positions. Another problem was the mounting of the microswitches. I tried with printed bolts in an early version of the switch, but they broke off too easily. Therefore, I'm using heat-set insert nuts with M2.5 screws. These insert nuts are so tiny, I found it convenient to pull them in place with a screw from the other side to make sure they are exactly upright before melting them in. For the assembly of the switching plane, I recommend to mount 2 of the microswitches first, then insert the switching wheel before mounting the other 2 microswitches. For the connection of one switching plane to the next, 2 printed spacers, M3 countersunk screws and nuts are used. On top of the stack, however, there should be the stepping module. The connections are done in a diagonal manner. In this way, the switch modules are stackable as much as needed. Before attaching the stepping wheel, don't forget to put an M3 nut and the printed washer in place. This nut is needed later for mounting the knob. Take care about the orientation of the stepping wheel if stops are used, as in my case, where I need to turn it one step to the right to allow the -1 position. And before finalizing the body with the cover plate, don't forget 2 more M3 nuts, or you won't be able to mount the complete switch to the front panel of whatever device you made it for. Now would be the right time to mark the required orientation of the switch and then mount the whole thing into the target device with another 2 M3 countersunk screws. As this video is just about the rotary switch itself, I'm mounting the knob right away. Okay, that's all for now. I'm going to show the assembly and test of the isolation transformer another time. Now I leave you alone with a speed run of assembling the big 12-switch version of the rotary switch. Maybe it's at least somewhat relaxing to watch. In the description below you can find the link to Thingiverse, where the whole FreeCAD project, the STL files, and a list of the external parts are available. Thanks for watching and see you next time.